In this section, we're going to be covering 1.3 from the free online textbook from OpenStax, and it corresponds to radicals and rational exponents. So the first thing I want to point out is this rule that you should know. So a to the m over n, so notice that is a fractional exponent, so that's called a rational exponent. You can rewrite that in radical form, where you take the root first and then raise it to the m, or you can raise it to the m first and then take the nth root. But either way, notice that m is the numerator, so that's the exponent, and n is the denominator, so that is the index or the root. So anytime you have a rational exponent, the top number is going to be the exponent, and the bottom number is going to be the index or the root. So keep that in mind as we go through this section. You might have to rewrite something. So for the first few, we're just going to simplify the expression. So for number 1, we're looking for the square root of 144. So first of all, you should know that if there is not a number written here, it's understood to be a 2. So you're looking for the square root. So what multiplies by itself 2 times to get 144? And so the answer to that is 12, because 12 times 12 is 144. All right, square root of 192. So actually 192 is not a perfect square. That means that nothing, no integer or whole number can multiply by itself to get 192. So in this case, all you're trying to do is simplify. So what you want to do, and this is just one way you can do this, you take the 192 and you make a prime factor tree. So 192, I see that the last digit is even, so I can divide by 2. So that would be 2 times 96. So 192 is used. 2 is prime, so I'm going to stop there. 96 is still composite. I can still divide it or break it down. So 96 divided by 2 is 48. Okay, so every time I'm breaking down a number, I'm crossing that number off. Okay, 48 is 2 times 24, and you just keep going. So 24, you can do 3 times 8. 8 is 2 times 4, and 4 is 2 times 2. So now I kept going until I have prime numbers. Remember that a prime number is a number that could only be broken up into one in itself. So you don't want to keep going at that point. Since this is a square root, and it's understood to have a 2 right here, we're looking for groups of 2. So anything that has a pair will come out of the radical. So on number 1, we could have broke this down into 12 times 12, and since there's 2 of them, the 12s come out as 112. That's how we get 12. So for this, I have a pair of 2's, and then I have another pair of 2's, and then I have another pair of 2's. So every pair comes out as 2. And then anything that does not have a pair stays under the radical. So this 3 is the only thing that is not crossed out. I forgot to cross out the 4, and does not have a pair. All right, so I have a 2, another 2, and another 2. So I have 3 2's. They're going to come out of the radical. And then I have a 3 that's left under the radical. And now I'm just going to multiply those 2's together. So 2 times 2 times 2 is 8. So 8 square root of 3 is the simplified version of the square root of 192. So get comfortable doing those. You should know how to reduce a radical. So number 3, this is similar to number 2, but notice here our index is 3. So we're going to work this the same way as we did the one above, except this time, instead of pairs, we're going to look for groups of 3, and that's because the index is 3. So 540, I know that that's divisible by 10, so I will do 10 times 54. It doesn't matter what numbers you use, you just break it down however you see. So you could have done like 2 and 270. That would be fine. Or you could have divided by 5. So 10 will break down into 2 times 5. Those are both prime. 54 will break down into 9 times 6. 9 will break down into 3 times 3. And 6 will break down into 3 times 2. So now I have all prime numbers at the ends of my branches. So remember that we had a cube root. So that means we're looking for groups of 3. So in order to come out of the radical, there has to be 3 of them. So notice we have 3 3s. That's the only thing that we have 3 of. We have 2 2s, but that's not enough. And we have 1 5. So anything that's in a group of 3 will come out of the radical. So that means 3 will come outside of the radical. And then 2, 5, and 2 are left under the radical. So we'll have 3 times the cube root of, and if we multiply that together, we'll get 20. So that's the simplified version of that radical. So no matter what your root is, no matter what your index is, you're going to do the same process. You just might be looking for different size groups based on your root or your index. Okay? So if you have a square root, you're looking for groups of size 2. If you have a cube root, you'd be looking for groups of size 3. If you had a fourth root, you'd be looking for groups of size 4, etc. All right, so for those first 3, we just had numbers. You could also have variables in your radical, and you need to know how to simplify those as well. So if it helps you to write the index down, you can. But remember, if it's not there, it's understood to be a 2. So if we just look at the square root of 4 and we ignore the y squared, the square root of 4 is 2 because 2 times 2 is 4. So that comes out as a 2. And then what you do with the variable is remember that you're trying to look for pairs if it's a square root. So I could rewrite this as 2 times 2 times y, because 4 is 2 times 2, and there's y squared means y times y. And then you'll see that I have a pair of 2's, so that would come out, and I have a pair of y's, so that will come out. So 2y out of the radical is my answer here. This simple way to simplify variables and bring them out of the radical is just to divide. So you're going to, let's say I had x to the 4th, y to the 6th, okay? And I know that this is understood to be a 2. So if the exponent is evenly divisible by the root or the index, then it can come out. So 4 is divisible by 2, that's x squared. 6 is evenly divisible by 2, that's 3. 6 divided by 2 is 3. So x squared y cubed comes out of the radical. So if it's evenly divisible, it just comes all the way out and there's nothing left over. You could have leftovers, however. So let's look at another example that I'm going to add in here. Let's do the square root of x cubed. So let's just keep it simple. Let's just do x cubed. Okay, so 3 is not evenly divisible by 2, because this is understood to be a 2. But 3 is bigger than 2. If we wrote this out in expanded form, that would be x times x times x. And you can see that we do have a pair of x's that would come out. We just have a leftover x. So what we would get is x square root of x. So the circled x's come out as this x, and the leftover x stays where it is. So what you're going to do here is you're going to divide. So how many times does 2 go into 3? 2 goes into 3 one time, and then your remainder is 1. The number on top is how many come out, and the remainder is how many stay under. So 1x came out and 1x stays under. Okay, let me do one more example like this with bigger numbers. So let's say I have the square root of y to the 13th. So the root or index is 2. So we want to know how many times does 2 go into 13. Well, 2 goes into 13 6 times, and then the remainder is 1. So 6 y's go out, 1 y stays under. So 6 y's come out. So y to the 6th comes out, and then 1 y stays under. And that would be reduced. All right, so the exponents, you're just dividing. If they divide evenly with no remainder, the whole thing goes out. If there's a remainder, then the quotient goes out and the remainder stays under. All right, so let's look at number 5. So for number 5, we have the square root of 300, a cubed, b to the 4th, and c. So first let's look at 300. So this is going to be 100 times 3. 100 is 50 times 2. 50 is 25 times 2. And then 25 is 5 times 5. All right, so now I'm looking for pairs since we have a square root. So I have a pair of 5s, a pair of 2s, and then a 3 left over. So the 300 is going to have a 5 times 2 on the outside of the radical and a 3 on the inside of the radical. Now I want to look at the a. So the a has 3. So I want to know how many times does 2 go into 3. So 2 into 3 is 1, remainder 1. So 1a goes out and 1a stays under. So that means I'll have a to the first out here and an a to the first out here. Okay, b. It's a fourth exponent, right? The exponent's 4, the root's 2. So 2 goes into 4 twice with no remainder. So b squared comes out and there's no b left under. And now last I have c. So c is only 1. If your exponent is smaller than the index, then it has to stay under the radical. So 1 can't come out if I need 2. So c stays under the radical. So to simplify, I need to multiply the 5 times 2. So 10ab squared times the square root of 3ac. Okay. Number 16. So now we need to add or subtract if it tells us to do that. So number 16, we need to add these. In order to add radicals, you have to have like radicals. So that means what is inside the square root has to be exactly the same, or you cannot add them together. So the way it's written right now, we cannot add them together. If I had 3 square root 2 plus 4 square root 2, whoops, I'm saying 2 and I'm writing 3. There we go, 2. See how these square roots are exactly the same? If that's the case, then you simply add the coefficients and leave the square root the same. So you would add that together and say you have 7 square root of 2. So what we want to do is see if we could reduce either of these radicals so that we can get like radicals. So 45, if I look at the 5, that's prime, so I can't simplify it at all. But the 45 I can break down into 9 times 5. And then the 9 breaks down into 3 times 3. And I can see I have a pair of 3's. So a 3 will come out and a 5 will stay under. So I will have 15 square root 5 plus the 7 comes down. I have to multiply that by the 3 that's coming out from this pair. And then the 5 stays under the radical. So 3 square root of 5 is the simplified version of the square root of 45, right? But you have to remember you have that 7 in front, so you've got to multiply the 7 by the 3. So now we'll have 15 square root of 5 plus 21 square root of 5. And see, now we have the same radical. So square root of 5 and square root of 5. So now at this point, we simply add the coefficients. So 15 plus 21 is 36, and then we leave the square root of 5 alone. So that's the answer to that. All right, number 7. We want to find the square root of this fraction. All you have to do is find the square root of the top and the square root of the bottom. So this is the same as the square root of 96 over the square root of 100. So 96, that's not a perfect square. 100 is, that's 10, right? Because 10 times 10 is 100. 96, we need to make a factor tree. And some of you will have a calculator that will do this. So if you have a calculator that simplifies your radicals for you, great, you can use that. But if you don't, then you need to know how to do it. Your calculator is not going to be able to simplify radicals with variables in it. So you will have to know how to do that. All right, so 96. Let's see, if I divide that by 2, I will get 48. So 2 times 48. And then that's divisible by 8. So you can do 8 times 6. And then 8 is 4 times 2. And 4 is 2 times 2. And 6 is 2 times 3. All right, so let's look for pairs. So I have a pair of 2's here. I have a pair of 2's here. I have a leftover 3 and a leftover 2. So I'm going to have 2 and 2 on the outside, and then a 2 and a 3 on the inside. And so that's going to be 4 square root 6 over 10. All right. So now what I want to do is try to reduce my fraction. So look, I have a 4 on the outside of the radical and a 10 that's out of the radical. So I can reduce those by a common factor. Those are both divisible by 2. So if I divide out by 2, I will have, so 4 divided by 2 is 2, 10 divided by 2 is 5. So I will have 2 square root 6 over 5. And that is as good as it gets. All right, number 8. So for this one, we want to do the same thing as before. So the first thing we'll do is we'll try to simplify. So square root of 3 over square root of 5. Now, 3 and 5 are both prime, so I can't do the factor tree. Here, the issue is this is not considered simplified if there's a square root in the denominator. So you want to get rid of the square root in the denominator. To do that, it's called rationalizing the denominator. You're going to multiply by another square root of 5. Remember that whatever you do to the bottom, you have to also do to the top to keep it balanced. So the fraction has to be equivalent. So if we do that, we'll get the square root of 15 over the square root of 25. And now look, the square root of 25 is 5. So it came out of the radical. That's why you multiply it by whatever you have, because it squares it, which takes care of the radical. So we'll have the square root of 15 over 5. This will not reduce because the 15 is under the radical and the 5 is not. So this is as simple as it gets. So in order to reduce, both things have to be either under the radical or out of the radical. Okay. Number 9. So we want to try to add these together. We do not have like radicals. So the first thing is to try to simplify the radicals. So 108, I can divide that by 2. That would be 54. Okay, and then I can divide that by 2 again, and I would get 27. All right, and then 27 is 9 times 3, and 9 is 3 times 3. So it's a square root, so I'm looking for pairs. So I have a pair of 2's and a pair of 3's, and then this leftover 3. So for the 108, I will have 2 times 3, square root of 3, and then I should have left room. because I have this x to the fourth, and the 4 is evenly divisible by 2. So that's going to come out as an x squared. Same here. So let me erase this. All right. So again, coming out, I will have 2 times 3, and x squared will come out, and then left over I'll have a 3. No x's are left underneath, again, because this 4 is evenly divisible by the 2. Plus, now I'm going to do the same thing with the 27. So this is 9 times 3, 3 times 3, a pair of 3's, a 3 left over. So I'm going to have 3x squared with the 3 left over. All right, simplifying, I'm going to get 6x squared times the cube, or times the square root of 3, plus 3x squared times the square root of 3. In the case where you have variables and radicals, they both have to be alike. So the variable has to be exactly alike. It is, right? They're both x squares. The radicals also have to be exactly alike, and they are. If that's the case, then you can add or subtract the coefficients, whatever the case calls for. Since this is an addition, I add them. So 6 plus 3 is 9, and I leave the variable and the radical alone. So that would be the sum of those two. So these problems can be very, very simple, but they can also be very complex depending on how much is kind of added to the problem. But the key is you do it the same way every time. You just simplify as much as possible. Try to get them to be like so that you can add or subtract them. All right, that's the end of this section.